Hello and welcome to the chapter The Geometric Distribution. So the geometric distribution is a discrete random variable, just as the binomial distribution. So for a discrete random variable, you have two properties. You know that the random variable takes only exact values, that is whole number 1, 2, 3, 4, 5, etc. And then the total sum of probabilities must be equal to 1. These two are very important for a discrete random variable. Now let's see how a geometric distribution is defined. So the random variable x is defined as the number of trials up to and including the first success in a series of repeated independent trials. So again, we have a trial, an experiment which is being carried out several times. So we have a number of trials and the trials are independent. That is, the outcome of a trial does not affect the outcome for other trials. And here x is the number of trials up to and including the first success. That is, we want to know how many trials there must be in order for us to obtain our first success. So the least number of trials must be 1. So here we have 1, 2, number of trial cannot be 0. Unlike binomial distribution where we could take the smallest value of x as being 0. So here the smallest value must be equal to 1 because here x is defined as a number of trial. So we can have number of trial to be 1, 2, 3, 4, etc. Here we have an infinite number of terms. And then we define our probability of success in a similar way, that is, as binomial distribution, probability of success is equal to p, and the probability of failure will be 1 minus p. Because it is a discrete random variable, we know that the total probabilities is 1. So we can obtain the probability of failure as 1 minus p. And p is constant for each trial. So let's now consider a situation in which we are trying to obtain a 6 with a fair die. So x is number of trials up to and including the first 6 is obtained. So if we write probability x is equal to 1, this means that a 6 is obtained on first throw of the die. This will give us 1 over 6. That is, our success is obtained on the first throw itself. So probability of success here is probability is 6 is obtained, and it is 1 over p is equal to 1 over 6. So probability of failure will be 1 minus 1 over 6, which gives us 5 over 6. Next, if we write x is equal to 2, probability that a 6 is obtained on the second trials. That is, the number of trials required for us to obtain a first 6 is 2. So if a 6 must be obtained on the second trial, that means that a 6 is obtained on the second trial. So on first trial, we will have failure. So we will have failure followed by success. So failure on first row. This means probability is 6 is not obtained on first row. First row, second row. So here a 6 is not obtained and a 6 is obtained on the second row. So we have 5 over 6 times 1 over 6. If we write x is equal to 3, this means that first, second, third. Here we obtain failure, 1 minus p. Here also it's a failure. And on the third row we obtain 6. So we will obtain 5 over 6 times 5 over 6 times 1 over 6. 5 over 6 to the square times 1 over 6. If we go on like that, suppose we have x is equal to 6. This means that we will have failure on first 5 rows followed by a success on the 6th row. So the probability will be as follows. So first, second, third, fourth, fifth. All these probabilities will be 1 minus p, 1 minus p, 1 minus p, 1 minus p, 1 minus p. And on the 6th row, here we will have our success. That is, a 6 is obtained on the 6th row and the probability will be p. So here we have 5 over 6 power 5 times 1 over 6. Here you will see a pattern is being formed. So when we have x is equal to 2, we have one failure. When we have x is equal to 3, we have 2 failures before the success. So it's failure power 2 times success. For 6, it's failure power 5 times success, probability of success, which is 1 over 6. For probability x is equal to 10, we will have 5 over 6. So we will have 9 failures before. So it becomes power 9. And then on the 10th row, we will get 6. So times 1 over 6. Similarly, we can say that for the off row, we will have r minus 1 failures. That is, we will not get a 6 on the r minus 1 rows. And then on the off row, followed by a success on the off row. So here for the r minus 1 trials, we will not obtain a 6. So the probability will be 5 over 6 power r minus 1. And then on the off row, we will obtain a 6. That is, the probability is 1 over 6. So this is the probability x is equal to r. So in general, this is what the probability for the first success being occurring on the off trial will look like. So if we have R is equal to 1, that is on the first trial we will have success, the probability will become P. Again, if R is equal to 2, that is on the second trial we will obtain our success, it will become 1 minus P, that is failure, followed by P. So we write P first, we will obtain P times 1 minus P. Here success is obtained on the third trial, so to failure, that is 1 minus P to the square times P. Success is obtained on the fourth trial, that is for the first free trial we will have failure. The probability becomes 1 minus P cube and then times P. For the nth trial, that is for the n minus 1 trials before the nth trial, we will get only failures. So we will obtain 1 minus P power n minus 1 and then times P, success being on the nth trial. So as you can see, the values of the probabilities, that is probability x is equal to R, these terms are the terms of a geometric progression. The first term is P. First term of this geometric progression is P, and then the common ratio R, is 1 minus P. Let's now consider the sum of the probabilities. So since it is an infinite series, we have the sum of the probabilities is equal to the sum to infinity of the geometric progression. So sum of all probabilities, which we write as summation of probability capital X is equal to small r, this will be equal to sum to infinity, and the sum to infinity, it's the first term, that is A, first term divided by 1 minus R, that is 1 minus the common ratio. So here sum to infinity, first term is P, we divide by 1 minus the common ratio is 1 minus P, we obtain 1 minus 1, 0, minus minus, this becomes P over P, which is equal to 1. So the sum of the probabilities in a geometric probability distribution is equal to 1. And again, this confirms the fact that it is a discrete random variable. Discrete random variable. Let's now consider the conditions for a geometric distribution. So X is said to have a geometric distribution, and X is defined by its parameter P if it meets the following criteria. First of all, the repeated trials are independent. Secondly, the repeated trials can be infinite in number. Thirdly, there are just two possible outcomes for each trial, that is success or failure. And finally, the probability of success in each trial, that is P, is constant. So to sum it all, we can say that a random variable X that has a geometric distribution is denoted by x follows geo with parameter p, p being the probability of success, and the probability that the first success occurs on the off trial is probability capital X is equal to R. This is the PDF for a geometric distribution. It is p times 1 minus p power r minus 1 for r is equal to, so the least value that the r can take is 1. So we have r is equal to 1, 2, 3. It can be up to infinity. Or we can write it also as p times q power r minus 1. Q, as you remember, it is 1 minus p. So that's all for this lesson. It was an introduction on geometric distribution. So see you for the next lesson. Bye.